Welcome to our new session of the Game Theory Seminar. So happy for people that are connected via Teams. I saw Sylvain Sorin at least, and happy also to have all our PhD students here. So it's my great pleasure to introduce Panayotis Mertikopoulos. Who is not only a friend, very close friend, he was also my postdoc. So I'm proud that he was my first postdoc, and now he's much stronger than me. And I'm proud of the career that he has at the CNRS as researcher, and hopefully we will see him often at the Moroccan Center of Game Theory. So this week he's teaching the last series of courses of this second trimester. So we had 12 courses in all topics of game theory, and this week it was about online learning and multi-agent learning and applications to convergence and non-convergence to Nash equilibrium. So the topic of today will be related to the course he's given at the Game Theory Center for the PhD program. So very brief resume of the career of Panayotis. So he did his undergrad studies in the US, Brown University, then his PhD in Athens in physics, then postdoc at the École Polytechnique when I had the honor to be his supervisor. After this, he integrated the CNRS, and now he's director of research at the CNRS in Grenoble, and with an amazing career. So if you look at his CV, you can see that he has at least 10 publications per year in the best conferences like ICML and NeurIPS, and the best journals like Math Programming, Math of OR, and he's also associate editor in the top journals of the field and the top conferences. So he's really amazing, and I think he never sleeps. That's why he's so productive. So now I'm give him the floor.
All right, thank you. You're exaggerating. The honor and privilege was mine, and the thanks are also mine for inviting me here in this great place. My second time in Morocco, yeah, I should start by apologizing to the poor students that are following my course, because I mean, I know you've already had 4 hours of this yesterday, 4 hours and change today, and now you will still get some of the same thing. So I will try to make it at least a bit more fun, and but there will be a lot of intersection with what you've already seen. I apologize for that, but I also have to, in a sense, well, it is a difficult audience to calibrate, because for some, I guess the topic is a bit new. For others, Sylvain is an expert on this, and he's following, and I'm sure he's ready to pounce. So. So if Sylvain pounces, this will be a lot of fun. So let's hope that I say something that annoys him. That way it's very fun. All right. So what I want to do with this talk is to sort of give some overview of what online learning in games is all about. This is to give some context for the subtitle. This is a very old field within the context of game theory. Even if you go back to Nash's original paper, he mentions at some point, you know, about the justification of Nash equilibrium through populations of agents that interact over time, and whether they ultimately converge to a Nash equilibrium. So many of the ideas that I'm going to be presenting today are definitely not new. They exist. They have been revisited, rediscovered time and time again over the years. Sometimes in the 80s, others in the 90s, early 2000s. And I would like to at least give some new results or a fresh take on some of these old questions that people have been asking in the field of online learning in games. All right, and I should say that the results that I'm going to present is basically due to a lot of junior co-authors that I've had the pleasure to work with, Victor Bon in Grenoble, Angelique Yano in Wisconsin, and Yaping Shi, who was at EPFL and is now in ETH Zurich. And I'm going to try to present a mesh of all of some of our results with these amazing people. So I'm gonna start by giving 2 examples of learning in games. All right, one will be very familiar to the poor PhD students following this course, again, because it will have to do with learning in finite games. The other is a bit newer, is intended for people that are already familiar with learning in finite games, and it concerns learning in stochastic games. And I would like to show how these 2 apparently very different things can be ultimately seen and examined with at least a common set of tools. All right. So the overall general idea for in online learning in games is that you have multiple agents, each with their individual objective. Okay, so these are like selecting a route from home to work. Their payoffs are determined by the actions of all agents. The agents receive these payoffs, they adjust their action, and the process repeats. This is the general gist of a repeated multi-agent decision process. And what we would like to see here is what the agent's long-run behavior looks like. Can I make this disappear or not? It disappeared. Okay, good. So if you were to write it out in a bit more detail, you have time, which evolves and which could be either continuous or discrete, and at each epoch, every player chooses, as I said, an action. They receive a reward based on the actions of all other players. Maybe they get some extra feedback, and the process repeats. Okay, and depending on whether you focus on continuous or discrete time, continuum or finite number of players, a continuum or finite number of actions, and the mechanism, whether the mechanism determining the rewards is endogenous, meaning it is coming from a game, or it is exogenous, determined by nature, you can get very, 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 very different models. And in this talk, I will focus more on the discrete time, the discrete context, which is closer to the algorithmic part of online learning in games, a finite number of players, actions. We will oscillate between continuous and finite, and we will always be considering endogenous rewards determined by some underlying stationary game-like mechanism. All right. So, as I said, I will start with 2 examples of this process. The first coming from finite games. In the context of a finite games, at every instance in time, every player picks a mixed strategy. I'm not going to specify yet exactly how, but they have a mixed strategy. They select an action based on this mixed strategy, and they observe something. This something could be, in the best case, the entire vector of mixed payoffs, meaning that they know exactly what they would have gotten for every one of their pure strategies against the mixed strategy of their opponents. So this is really a lot of information. Then maybe they are only able to observe or otherwise compute their pure payoff vector, which is they can counterfactually compute the payoff of their actions against the actual actions employed by the other agents. Okay, this is still not trivial to compute, but at least it is less demanding than having to observe the entire mixed payoff vector. Or maybe, and this is by far the most difficult case, when the players only observe the realized payoff, the payoff of the action that they picked, and that's that. They have no further information about the game. All right. So In each case, they have to use this information in order to feed it into some update rule, which will then allow them to update their mixed strategy and then run this loop over and over again and hopefully converge to some reasonable state. All right. Now, in terms of feedback, as I said, the type of feedback is going to be very important in our results. And I mentioned 3 cases where they observe from best to worst, they observe mixed payoff vectors, very powerful but very difficult to obtain. Pure payoff vectors, less difficult to obtain, but still okay in terms of power. And by far the hardest, as we said, the bandit or payoff-based case. All right. I'm gonna skip this because what I'm the key element which of course distinguishes the bandit from the other 2 cases is that in the bandit case you only have access to a scalar. You don't have access to vector information. So you will need to somehow reconstruct the payoff vector of the players, and you will need to always construct some estimator using which you will hope to obtain some information about what's going on. All right. Now, assuming that somehow you are able to either construct or otherwise compute such an estimator, a very popular algorithm to run is the so-called exponential weights algorithm, or which is basically a template. It is also known as hedge or EXP3, depending on the specific type of feedback that you have. And how does this work? It tells you that for every player basically aggregates the payoff information that they receive. Okay, they aggregate this estimate of the payoff vector at time t. Then they take a strategy which is basically proportional to the exponential of this vector. They choose an action based on this. They choose an action based on this mixed strategy. They get their action. They get their payoff, and the process repeats. All right. So this is a standard algorithm for learning in finite games, where again the main idea is you aggregate payoff information and you employ an action with probability which is exponentially proportional to this aggregate payoff. All right. The thing is the main question here is whether this algorithm, which I'm not going to motivate, it has a very long history in many different fields, whether this algorithm converges to a Nash equilibrium, to a stable, because this is the most widely used stability and solution concept in games. Just to define it clearly, Nash equilibrium in this context means that no player has an incentive to deviate. In terms of mixed strategies, it means that X star is Nash equilibrium whenever the payoff to each player who uses their equilibrium strategy is greater than or equal to their payoff if they used any other, if they deviated to any other strategy. All right. Now, there are all sorts of different configuration of the support. Is it okay? Okay, all right. The equilibria that if you have full support, if the equilibrium has full support, this is mixing all strategies. If it is only if the support is a singleton, then you have a pure equilibrium. And if you have a pure equilibrium where the defining equality is strict, then in that case you have a strict Nash equilibrium, in which case every player has a unique best response. All right. The reason that I'm mentioning this is that depending on the support of the equilibrium, you have a different configuration of the of the payoff vector at equilibrium. If you have a fully mixed Nash equilibrium, then the payoff vector is going to be perpendicular to the plane, to the affine hull of the simplex. If you have an equilibrium which is mixed but not fully mixed, it will still be on the normal cone and it will be outward pointing. And if you have a strict Nash equilibrium, then in this case, the payoff vector at an equilibrium is going to be strictly outward pointing, where strictly here means that it is going to be at the top, in the topological interior of the normal cone to the simplex at said point. All right. Why am I mentioning all this? Because we will see again the same type of structure in the case of stochastic games, and different equilibria will have completely different learnability properties under, for instance, the exponential weight algorithm that we saw, based on where they are on the simplex. The location of the simplex, and in particular the configuration of the payoff vector, will play a huge role on the stability and learnability properties of each equilibrium. All right, so if anything, I want you to keep in mind this. Learning in finite games, you have this very widely studied algorithm known as hedge, exponential weights, whatever. It's whether it has good rationality properties relative to an equilibrium will depend primarily on the configuration, on the support of the equilibrium, and whether it is strict or fully mixed. All right, that's the main idea, and what I would like to, what I will try to justify later on. Which is basically what I am trying to say here. The question that we will try to answer in this context is, when does learning converge to a Nash equilibrium? Which equilibria are more learnable in a sense than another? And what other types of behavior emerge in the long run, and whether these types of behavior are rationalizable, or rational, or what have you. All right. Now, this is the first, if you want, example that I wanted to mention, which has to do with finite games. The other has to do with stochastic games. Now, stochastic games are a very different beast. I will be looking here at stochastic games that are played over episodes. So how does a stochastic game evolve here in this context? You have the world, which is at a certain state, all right, or nature, which is at a certain state. Based on the state of the world, every player selects a mixed strategy. How do they do that? They have a rule, a policy that is mapping the state of the world to a mixed strategy. All right. Based on this mixed strategy, every player selects an action. All right. They receive their rewards, they get their payoffs, and then, depending on the actions of all players, nature transits to a different state, S tau plus 1. And once nature transits to a different state, which again depends on the actions chosen by all players, then this process repeats until at some random time, there is a clock that rings and says stop. So with a certain stopping probability, this game stops. All right. This is an episode of a stochastic game, which is in computer science now, for some reason which is beyond me, these are now referred to as Markov games. But anyway, if you see it in the literature, it is this. All right. So here, again, what you would like to see here is that you would like for players to select good policies. All right, policies, again, mapping the state to a mixed strategy, and the mixed strategy determines your choice of action. Now, how do you evaluate the performance of a policy over an episode? You just take the expectation of the aggregate payoff that you got over the episode, and you take the expectation over all possible trajectories that you could have. All right, this is the value associated to the policy. All right. Now, because there is also this random time, I mean, at every point, the game has a probability of stopping. There is inherent in this sum over here. There is an inherent discounting factor, which I'm not showing explicitly. But this also means that this function here, this value function here, in contrast to what you have in normal form games, it is no longer linear. The dependence of this value function on the policy of the players can be quite complicated. All right. And so what you would like to do is you would like to find a policy, you would like some learning process that converges to a policy which is in some sense an equilibrium. All right. Now, what would be an equilibrium policy in this context? Again, I'm oversimplifying certain things because I don't want to get into the details of different type of equilibrium policies that you can have in stochastic games. But basically, the equilibrium here is a policy which is resilient to unilateral deviations. No player has an interest of deviating from this policy if all other players stick to it. And when I say they have no interest, I mean relative to this value function upstairs. Okay. All right. So that is the notion of a Nash equilibrium in this context. And what is interesting is that you can get in stochastic games, which have a completely different structure than finite games, you can get a characterization of Nash equilibria, which is very much similar to the characterization that you had in the case of finite games. In the case of finite games, a mixed strategy profile is at Nash equilibrium if and only if the corresponding payoff vector is outward pointing. All right, here you have again this first order variational characterization. This is known as a Stampacchia variational inequality, which tells you essentially that a policy is Nash if and only if this the vector field, which is constructed by taking the unilateral gradients of the player's value functions, is outward pointing. This, in essence, I submit to you that it is the same as in the case of finite games, because in finite games, the mixed payoff vector that is outward pointing at a Nash equilibrium is exactly the unilateral gradient of the player's mixed payoffs. All right. So here it is exactly the same thing. The only difference is that what goes into this variational inequality is not the player's payoff vectors, but the unilateral gradients of the player's value functions. Other than that, other than the definition of the field, if you want, which ultimately describes the game, everything is the same. And indeed, the most popular algorithm that we have in order to try to solve stochastic games, find the equilibrium of stochastic games, revolves around updating updating the player's policy by estimating the policy gradient. And this is why this algorithm is called the policy gradient algorithm, because what it does is if players are you have a stochastic game which is played in repeating episodes. So you play an episode, then you play another episode, then you change your policy, you play another episode, you change your policy, you play another episode, and so on and so forth. And your policy at episode T, in order to update it and go to episode T+1, you just take a policy gradient at the policy where you are, or you take an estimate thereof, you take a step along this policy gradient, and okay, maybe it happens that you go out of your policy space, you project back. Okay, this is what this projection here is all about. All right, and again, we have the same sort of setup as we had in the case of finite games. full information here means that you have access, that you can somehow compute the gradient of the individual gradients of your value functions. If you cannot compute them precisely, but you can only compute them up to a certain up to a certain random error, then you have access to a stochastic gradient. And if the only thing that you know is the payoff that you get at any instance during the realization of an episode, then you can use what is known as the reinforce algorithm in order to get an estimate and in order to get a stochastic policy gradient from this payoff-based information. Okay, so if you look at it from a high level, the situation is pretty much the same as in normal form games. Again, you have a characterization of Nash equilibria which is done in terms of some vector field which is defined in terms of the individual payoff gradients of the players. Again, the algorithms that you use are based on aggregating this payoff gradient information and then doing some projection. In the case of policy gradient, we're doing a Euclidean projection, and in the case of the exponential weights, we are doing some sort of skewed Riemannian-like projection in order to get back to the simplex. And in both cases, what we want to study is whether these algorithms converge to an equilibrium or not. And again, as in the case of finite games, this is a spoiler alert for the sequel. We will see that the structure, the support of the equilibrium, the payoff structure of the equilibrium of a stochastic game plays a very important role. So if it is a mixed equilibrium, then always the individual payoff gradient is outward pointing, and you have a subclass of deterministic policies that are at equilibrium, which are known as strict equilibria, in which case the individual payoff gradient is again at the interior of the normal cone. All right, so topological interior of the normal cone. So again, even though the context is completely different, look at from a high level, you sort of get the same elements, okay, in this story. And the idea is whether you can somehow extract something from this similarity and develop a sort of a unified framework with which to address the question of, when does learning lead to a Nash equilibrium, when does it not, and what other types of behavior can emerge. All right. So this is what I want to this is basically the main gist of what I want to show you today, sort of an attempt at such a unified view. And this starts from the observations that both of the games that we saw, even though, it is a finite game or a stochastic game, well, they have some deep underlying similarities. In the end, we have continuous control variables in both, mixed strategies in the case of finite games, policies in the case of stochastic games. And in both cases, as I said, learning is driven by the player's individual gradients. Mixed payoff gradients in the case of finite games, policy gradients, individual value function gradients in the case of stochastic games. All right. And this is essentially what defines the main ingredients of our approach. We will be looking at games with continuous action spaces. All right. And we are going to be using, in both cases, a sort of an algorithmic framework that encapsulates both policy projection, both policy gradients with Euclidean projections or exponential weight type algorithms. This is what we are going to call a regularized learning algorithm. And the tools that we're going to use to analyze these algorithms in this general framework will be based on a field which is known as stochastic approximation. And this is what we're going to use in order to get our results. All right. By the way, I've been talking. I have well, I cannot see on Teams whether there are any questions. If there are, please shout. But also here in the amphitheater, I mean, please shout, because you know, it's more fun that way. All right. So this is what we're gonna try to do. We're gonna try to mingle all these ingredients into a unified stochastic approximation framework for studying learning in games. All right. So each ingredient, one ingredient at a time. We start with continuous games. A continuous game consists of the following primitives. We have a finite set of players. Each set has a closed convex set of actions. All right. And then each player has a payoff function, which depends, which is determined by the actions chosen by all other players. All right. Again, these actions here, which are now continuous, in the case of finite games, these are the mixed strategies. In the case of stochastic games, these are the policies. All right. So this is what I'm just saying. But of course, this class of games is actually much more general, because you have a lot of other games that do not that have no relation to a continuous game. You have splittable atomic congestion games. You have auctions. You have Cournot oligopolies. You have applications in ML on generative adversarial networks, on GANs, etc., etc. All right. So this is going to be our framework. And the equilibrium concept that we're going to be using is going to remain unchanged. It is going to be Nash equilibrium. So an action profile is a Nash equilibrium whenever it is resilient to unilateral deviations. No player has an incentive to deviate based on their individual payoff function. And the key element that we will be using here is the players' individual payoff gradients. This is what defines this vector field here. Essentially capture all the information which is which defines the game. Why? At least with respect to Nash equilibria. Why? Because if an action profile is Nash, then it has to satisfy this first order stationarity condition, which is a Stampacchia variational inequality. This is a first order stationarity condition. And for the moment, I have made no assumptions about the structure of the payoff of the player's payoff functions. If the player's payoff functions are individually concave, meaning that they are concave, that the payoff function of player I is concave in the action of player I, in that case, then this implication is an if and only if, meaning that an action profile is Nash, if and only if this variational inequality is satisfied. All right. Okay. Geometrically, this variational equality again says the same thing that we've seen over and over again. It simply says that the individual payoff gradient at equilibrium is always outward point. Well, okay, yes, true. Assume it is C1. Yes. When I said I make no assumption, I meant a structural assumption, not regularity assumption. Structurally, I was referring to convexity and all that. Regularity, take it as regular as needed. That's not the lack of regularity is not going to be our problem here. Yeah. Yes. Mm-hmm. It is not. Yes, that's a great observation. Thank you. It is not individual concave, but still there is this equivalence between Stampacchia and Nash. Now, by the way, I have to say that in the context of stochastic games, the reference that I know for this is quite recent. I have the feeling that this is a much older result. So if you have a good reference for it, if you have an older reference, I'm very much, I would very much welcome it. All right, because yeah, this is not like I don't know too much about the history of that. All right. Okay, I would be very welcome. Tell me so that I'm not missing an important reference. Any other questions? All right. Actually, just to give just to give a bit more a somewhat more detailed answer to Julian's question. The underlying assumption for me is that the games here, every game that I will consider, has a Lipschitz gradient. And if you want to be more meticulous about this, because I'm only assuming that the payoff function are defined on a closed convex set, what I'm actually assuming here is that the Clark subgradient has a continuous selection, has a Lipschitz continuous selection. Okay, this is if you want to get deep into the regularity aspects of the question. All right. Now, so first ingredient was the game and the individual payoff gradient. Second ingredient is the type of feedback. So in terms of feedback, I will assume that players, maybe they don't have access to their full individual payoff gradients. They are not able to compute them because they don't know the game, but they have access to at least a black box model for it. What is a black box model? It is an estimate which is accurate up to some zero mean error, UT, and possibly some leftover bias or offset. All right. And to control, to have some control about these quantities, I will be assuming that the variance of the noise is bounded by some parameter, sigma squared, which could depend on time itself. Maybe observations get better over time. And the bias itself is controlled by some big T, which is the maximum bias that I could have. All right. So this is going to be my feedback, my black box model for the information that players have. If I have no noise, this should be UT, not BT. If I have no noise and no bias, then I have I know the full I have full gradient information, so that's the best I can hope for. If I have no bias, and I have noise which is with finite variance, then I have what is known as a stochastic gradient. This is still okay. All right. And the hardest case is that maybe I only have access to payoff-based information, in which case I would need to construct an estimator for the gradient based on this information. And here there is there are many ways to do this. The estimator that I'm showing here gives you an estimate for the payoff gradient, which has an offset of which has a bias of delta t. The way you do it is you look at xt, you play a nearby action of the one that you were intending to play, you observe the payoff of this nearby action, and then you construct this estimator. Di here is the dimension of your ambient space. And this estimator, which is known as single point stochastic approximation, or SPSA, has a bias of the order of delta t. Delta t is the parameter that you're stepping here in your perturbation, and a variance which is of the order of 1 over delta t squared. All right, and so you will be hoping to basically balance these two terms over time in order to get some good results. All right, so again, these are all examples, and what we showed before about finite games and stochastic games, polish gradients, reinforce, log tricks, all that are other examples. So now, for the actual dynamics that we're going to use. All right, they are going to be based on the same idea that we had before. We are aggregating gradient steps, where the gradient step, again, could be noisy, could be coming from this black box model, and then we are using some generalized projection scheme to get back to the our feasible region. What does this mean? It means that given this auxiliary dual variable, which is coming from the aggregation of payoff steps, we are defining a generalized projection via this recipe here. If it looks a bit weird, then the reason that I am calling it a generalized projection is that if you put here in terms in the place of h, which is called a regularization function, if you put here just Euclidean, square distance, 1/2 x squared, then you get the ordinary Euclidean projection. But you don't have to use the ordinary Euclidean projection. You can use an arbitrary regularizer as long as it is continuous and strongly convex. All right. This policy, this general policy, is a generalized version of a family of policy which is either known as follow the regularized leader, at least in online learning. In convex optimization, they are based on dual averaging. They are also related to mirror descent. There is a whole dissertation that can be written about these type of policies. But the important thing is that take me on faith, because I don't want to get into the details of this, is the following. If depending on your feasible action sets, on your action sets here, and the choice of regularizer, you can recover exactly the frameworks that I showed you before. So for instance, for learning with exponential weights in finite games, your xi's here are simplices, and you recover the exponential weight algorithms by picking the regularizer to be the Gibbs entropy, x log x. All right. If you want to recover policy gradient in stochastic games, then your xi here needs to be the simplex to the power of simplex to the power of s, where s is the state space of the stochastic game, and you take h, since we are talking about Euclidean projections, where you take h to be 1/2 x squared. All right. And again, this algorithm here is sufficiently flexible, thanks to the because the black box model that we are using here is really very flexible here. This model is also sufficiently flexible to include some other algorithms like the extra gradient or optimistic mirror descent and things like that, where I will you simply need you basically take an intermediate step to get a better estimate of the gradient that you would have faced if you had already taken a step. This is a bit complicated. Yes, question. Q learning. You can recover Q learning. You can recover Q learning if you change this update step. If you change this update step to include a discounting, so you need to write this VT and then take out lambda times the score. Yes, I think you can. Yes. 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 You're learning within the episode. I understand. I understand. So first of all, yes, the context is different. I agree, but but forget about the game here. Forget that T would refer to an episode. Okay, the question is whether you can recast Q-learning as a stochastic approximation algorithm of this general form. All right, and I am saying that I believe that you can if you change this step over here. Because if you there is a 2005 paper by David Leslie and his advisor Sean Collins, where they did exactly that. If you look at their algorithm in their paper, which is individual Q-learning, okay, it is in the context of a game, but you can, as you say, take it in a single player, no problem. The algorithm that they have is exactly this. You have v hat t minus the score inside, okay, and as you very correctly say, this T no longer represents the episode, but this is the time until because you go on forever and you discount. Okay, so mathematically you can up to this change. Okay. Right. Any other questions? All right. Okay. So I'm gonna skip those examples, and sorry. What I want to do, sorry about that. I want to move a bit forward because we are ending at 4:30, right? Okay, so we have 10 minutes. So let me. Sorry, I got lost here. Right. Now, forget this. This is the image that I wanted to start with. Okay. If you run, for instance, one instance of this algorithm, which is the exponential weight algorithm with bandit feedback, all right, and you run it in an ordinary finite game like Battle of the Sexes, what you will see is that the evolution of the algorithm, which are these blue lines, sort of follows these green lines, which are themselves the flow lines. These are the solutions of a dynamic of the mean field limit associated to the algorithm, which is just the limit that you get when gamma goes to 0, in which case you get a dynamical system. These are the solutions of this system. All right. Now, the thing is that you will notice that whenever the system is, whenever the continuous time dynamics are attracted to a certain state, then the same thing more or less happens with the corresponding discrete time trajectories. On the other hand, if there is no attractor, so here I'm showing what's happening in matching pennies. In matching pennies, the trajectories of the continuous time dynamics are periodic, so they do not converge to anything. All right, not to a set, no nothing. They always return to where they began. In that case, you see that this tessellation, the behavior of the algorithm is now basically all over the place. Okay, and it is not quite periodic like the continuous time limit, but it has this recurrence property in the sense that it always returns close by to where it began. All right. Now, you can see this in other games where here you see in this game all continuous time trajectories actually move in this phase, and then they circle around it, and then the continuous time, the discrete time algorithm also does the same thing. It moves towards this phase, and then when it reaches close to this phase, it becomes recurrent on this phase. All right, so I'll skip this because this is too fine, and I would just like to see what we can if we can make this precise. And indeed, what you in order to quantify what we said about convergence to a certain set in the stochastic context of these algorithms, you say that a set, not necessarily a point, a set is stochastically stable if whenever you start close enough to it, you remain close enough and you converge to this set with arbitrarily high probability. All right, this is the definition of stochastic stability in this context. The definition of stochastic stability is that if you start close enough, you remain nearby with arbitrarily high probability, and if you also eventually converge to the set in question, then this is stochastic asymptotic stability. All right. Now, what is the result? The result is the following. If you have a set which is an attractor of the continuous time dynamics, all right, of the mean field dynamics, like the strict equilibria that we saw here and there. This means, this means that for the continuous time dynamics, it attracts all nearby initializations. You can ask, is this the same? Is this the same? Is this also true for any of these algorithms that we consider? Is this true for policy gradient? Is this true for exponential weight? Is it true for all for this entire class of dynamics that we consider, this regularized learning class of dynamics? And here, the answer will depend greatly on the various parameters that go in the algorithm. You have the step size of the algorithm, you have how big your bias can become, and you have how big the variance of the noise can become. All right, and this theorem basically gives you the recipe, the conditions under which a stochastic approximation, under which an algorithm with parameters like that shares the same attractor as the replicator dynamics. As the mean field, as the mean dynamics. No, I didn't. I only said that they are the limit as x goes to, as the step size goes to 0. But they are very easy to write. They're very easy to write down. They are simply, the mean dynamics are these. Y dot is vi of xt, and xi of t is qi of yi of t. All right, thanks. So yes, what I want to say is that if these conditions on the step size and the growth of the statistics of the noise of the error are satisfied, then an attractor of the continuous time dynamics is also stochastically asymptotically stable under any one of these regularized learning algorithms. Okay. Yes. Though yes and no, because there are some hidden theorems here. So, for instance, if you have if you have an extreme point which is asymptotically stable under a q, then it will be asymptotically stable under any q. All right. If a phase, I said a point. if you have a phase which is asymptotically stable under a certain Q, then it is asymptotically stable under all the Qs. Not very easy to prove, but you know, it depends. It depends. Now, yeah. So this is what I want to close with, because this result is can be seen as good news, right? Yes and no. Yes and no. You have to be very careful with the type of this result, and I want to show you that this can actually also be a very, very negative result. All right, and here I want you to consider a game which is almost bilinear. So you take the game of min-maxing the product x1 times x2. Okay, very, very simple game. 0 is the Nash equilibrium, the value is everything for this game. And I add just a little perturbation, a little polynomial perturbation to the value function of the game. All right, so instead of min-maxing x1, x2, I min-max x1, x2 plus this function which only depends on x2. It is a very light perturbation, okay? And epsilon here can be arbitrarily small, 10 to the minus 4, 10 to the minus 8, whatever. So if you try to look at this game, well, this game is no longer convex concave, all right, because of the perturbation. It still has a unique critical point at the origin, but the thing is that all regularized learning algorithms no longer converge to this critical point, but they converge to a certain specific limit cycle from all initial conditions. If you run learning in this game, this is what you will end up with. So no matter where you start, this white point in the middle is the equilibrium, is the critical point of the game. No matter where you start in all the space, every trajectory of these regularized learning algorithms will end up coalescing into this white limit cycle over here. And this is true whether you run stochastic gradient or stochastic extra gradient, or no matter which of these regularized learning algorithms. All right. So this result is at the same time a bless and a curse, but it also highlights the importance of understanding the structure of the limit of the attracting limit sets of the game under a certain dynamical class, and to at least understand where they are. So this is actually what I would like to. Whoops! I jumped to the appendix. Sorry. This is what I would like to understand. First of all, the structure of the attractors. What type of where can we encounter attractors, for instance, in a finite game? Where can we encounter attractors in a stochastic game? Okay. Here, well, I have a conjecture, which is that at least in finite games, an asymptotically stable limit set, so an attractor, can only live on the boundary. All right. I have a lot of evidence about this conjecture. I cannot prove it, but if you can, you know, I'm buying you lunch. All right. I said it occurs at the boundary. It lives in the boundary. I'm not saying that the entire boundary is an attractor, because if the thing is that with all these toolbox would give you a very powerful way of predicting the outcome of all this general class of algorithms that we have for learning in finite games. Because if you prove one result for a dynamical system, then you immediately get it for all the algorithms, independently of the feedback assumptions that we have, whether they are run with perfect payoff information, stochastic payoff pure payoff information, bandit feedback, etc., etc. Sorry, I don't have such a conjecture. I don't understand stochastic games, so I don't put conjectures about stochastic games. I don't understand finite games either, but you know, at least that conjecture I understand. All right. So thank you.
Thank you, Panayotis. Great presentation. So any question from Teams people? Sylvain? If you hear me. But I saw many connections. No question from the... So it implies that the talk was clear. So from the audience, from the students.
Thank you for the talk. So my question is a bit general. So in the course of stochastic games, we have seen some Q-learning algorithm. So I'm wondering if it can be generalized over multiplayer stochastic games.
I have seen papers that are doing exactly that, like multiplayer Q-learning for I believe always discounted stochastic games, which is the same. I think Mohamed Sayin and David Leslie again and Assos Daglar have a paper about exactly this for stochastic zero-sum games. Sorry? Yes, but they are studying multi-agent Q-learning for this class of games. Rida with Luca, you did potential games, if I remember correctly, and zero-sum with Q-learning. Not Q-learning, fictitious. Yes, you did fictitious. Okay. Okay. I think I've seen somewhere a follow-up for Q-learning, multi-agent Q-learning stochastic games, or stochastic potential games. So stochastic potential games is a stochastic game, not for which every stage game is a potential game, but for which the entire stochastic game admits a potential function. So it's quite restrictive. But I don't remember the authors. But for sure it is something that has been studied, though not sufficiently well understood because the problem is very difficult. The problem is quite difficult. Yeah.
Let me complement this answer. So there is a difference between learning as he in stochastic game as he presented, where you play the stochastic game, then you repeat the stochastic game. So it's a repeated stochastic game. You can also learn during the play in the stochastic game. So the stochastic game will never end and you learn during the play. So for example, the Q-learning papers he's mentioning are doing this, okay? And you can show that they do not converge always to equilibria. However, you can have another process similar to fictitious play or smooth fictitious play in which you may have convergence to equilibria in zero-sum and identical interest stochastic game. Knowing that in the finite case, there is only one state, fictitious play only converge for these two classes of game plus monotone games. Okay. So if you are interested by this topic, I can send you a PhD of one of the students I supervise on that, and I send it to Omar. Otherwise, other questions?
So if I understand you, in this framework, you only study first order dynamics, and what I was wondering is if, like, you add higher order terms, can you get better? Can you get, for example, some characterization of two equilibriums? Like, do you have the same problem for do you have the same problems of the cycles instead of convergence, or do you get better convergence if you add the higher order terms?
Yeah, higher order in space or in time? I mean, because you could have higher order, meaning that you look at higher order derivatives, like the Hessian, and you try to do something like Newton's method, or you could do higher order in time, where instead of taking a first order differential equation here, you try to model a second order equation. So did you have, when you said higher order, what did you have in mind? Okay. Well, neither of them has been studied at the same extent that first order methods have been studied. Okay, so let me start with that. The reason for methods that are second order that are second order in space that involve Hessians is that in general computing a gradient is difficult. Computing a Hessian is often impossible. All right. So even though in optimization, convex optimization, for instance, second order methods had been like super popular up to a certain point, exactly because they offer better convergence rates. The moment you start stepping into situations with very large action spaces, with very large dimensionalities, they become completely intractable. And this is especially so in the context of stochastic games, because there you have your state space can make gives an exponential dependence. It gives you an exponential dependence in the dimensionality of the space, so it is very difficult. That is one reason that second order in space is not super has been studied in this context too much. Another is that in order for second order methods, for higher order methods to work well in optimization, you have to have the second order derivative has to be positive definite. So it works very well in convex optimization, not so much in non-convex problems. And here, when you have the vector field that is not even coming from a potential, things are even more complicated, because it could actually give you a search direction which is opposed to the individual payoff gradient. So for all these reasons, second order in space methods in games, not so much. Second order in time methods, if you're talking about rather in there have been some papers on that. Rida has a couple. Okay. And the properties, but I would say that they have better properties with respect to convergence to strict Nash equilibria. What do I mean by better? In the sense that they converge faster, and this is true even in discrete time. Even with bandit payoff information, they converge at a double exponential rate instead of an exponential rate. But whenever you have cycles, they perform worse. So in matching pennies, first order methods cycle, they are periodic, but if you run a second order in time method, then this would actually spiral out of control and converge to the boundary. So yeah, there's no magic bullet. Yeah. All right.
So we're going to stop because Panayotis is tired, and I think we will keep questions for after during his week here, but he will be visiting us often, so we hope. Thank you, and see you next section.